Last Wednesday, we already have the performance measure, and we have this. So we have this system size. And also we have the corresponding system time or waiting time because of Litto's law. All right, and actually we have the relationship if we have a queue. So we have a time in queue and also service time. Service time actually we can have the mean service time, but we can have 1 over mu normally. So we have this. All right, and if so, then we can have WQ. Right, this one. And once we have a WQ again, we can have the Litto's law. All right, so I do not follow the way to derive the full performance matrix. In fact, the task will try to rewrite LQ again and then apply Litto's law to find this, but I reverse it. So we have the way to have the full performance measure. Once we specify 1, or maybe we derive 1, and then we can have the results. Well, that's it. So that's MM1. And later, similar relationship can be applied to the generalized system. Later, we can let you know it is called MG1. But before we go, we have MMS queuing system. MMS says, oh, we have S servers. All right, S servers. Well, if so, what it means, we have 1, 2 to S. So we have S servers. As for the queue, infinite size. Well, so how to have the state transition diagram? Look at this again. The maximum rate. The max service rate, we have S multiply mu. So state transition diagram looks like this. Maxima, so if we have 2 customers, only 2, because 2 customers will be served. So rate 2 multiply mu, 3 to S here. And so that someone reach the maximum rate as mu. All right, so this is a way to have the state transition diagram. And this time I emphasize the state transition diagram. I think based on the derivation for MM1, you will know how to have the state transition or balance equations. So based on the balance equation, then we can derive. So I skip some details. Based on the balance equation, we can derive this. P of I. And once we have a P of I, how to have the system length? Same. We have I, 0, I equal to 1, 2 to the other. So this equation is the same. And it can be proven we have this one. So I do not check it further, but at least I already have the way how to have the calculation. Based on the steady state equation, then we can find this. Once we find this again, we can apply Little's law. And Little's law over rate. So again, we can have this. All right, so follow that way, we can have this one. Well, of course, so this one, maybe it is not really direct, so this time I follow this. If we have a Q, we multiply I minus S, because here we have a server, 1 to S. So minus S, and then a start from S, and then we'll stay in Q. All right, so this one, find it, then again, apply Little's law. So we have this result. All right, so this is MM1. Because of the derivation from MMS, because of the way to derive the result from MM1, so I go through quickly and allow you to know, oh, okay, follow the way, then we have the result, so MMS. So that's it. So I have the extension to MMS. And about this, let me know your status. Any questions? So that I have 1 minute to check. All right, so not finished, raise your hands. No, right? So let me stop the timer and go to the next one. And next one is attendance checking. Go and provide your student ID and name. So again, let me make sure. Not finished. Okay, so next one. And next one, actually, I upload the video to YouTube, even it's really late, maybe near midnight, right? And we have an MG1. All right, and of course, you can check the video for sure. So here, we have an MG1, and actually later, I have the overview of the remaining part for the MG1 queuing system, so this one. And after that, I provide the supplement to the MG1 queuing system, the approach employed by the textbook. It is called this one, matrix geometry approach to MG1. And in fact, we can have an alternative. So we have a mean value approach. So you can check the 3 videos. All right, now let me check this. All right, so of course, feel free to check it, but we have these questions. First of all, answer the following 2 questions. First one. If we have MM1, And we have MD1, so queuing delay. Compare the queuing delay, the formula, and which one larger. All right. And the second one, MG1, MD1, and MM1. If you are asked to apply the queuing model to analyze the system code, ARQ system, which one you think well should the analysis of the ARQ queuing system, and what's the reason, what are the reasons? All right, so about this, allow you to have 5 minutes to discuss with your neighbors. Okay, and again, readjust the table so that you can get together to discuss this. And feel free to check the video if you don't have any idea. At least you can get closer. So, oh, belong to good too. And actually, some results are included in the video. Sure, you can check it. So feel free to discuss with your partner. So move your table so that you can get closer. So where is Alex? Okay. So you mean you want to find me this Thursday, right? Past 4. 4 p.m. 4. Tomorrow? Oh, Thursday, sorry. 4. Ah, Thursday? Let me check later and respond to you. Thursday or Tuesday? Later I check it. If you have 3, you can try to have this way. No, switch. Rotate. No. Rotate. Yeah, this one, right? Yeah, sure. Yeah, that's correct. Yeah. So up to now, any idea about the two questions? And actually, you are asked to answer on Paul article before you go. Let me have maybe so we have 4 and sorry, not this one. And go on, focus on problem 1. And select 1 to serve as the presenter. What's the result if you compare the two systems? And go 2, the same. All right, problem 1, go 2. And later, one of you serve as the presenter. Go 3 and 4, focus on the second problem. 3 and 4, second problem. Ready? So right now, for the presenter, start the Skype. So let me start the Skype. So for the presenter of this, you need to join Skype. And this time, I set myself to mute. So later, if you are the presenter, you can turn on your microphone. And of course, my microphone here as well. All right, so go 1 and 2, problem 1. Which one ready? Ready? Okay, join the Skype first, sure. And go 2, ready? Okay. And go 3 and 4. Any team ready? All right, so that you have for 3 minutes further. Previously, I think you know the problem, right? Should we have the problem again? The problem, take a picture for this page, and so they have your own problem. All right, so this one, group 1. Okay, so group 1 ready and mention how you have the result and how to compare the result. Who is the presenter? 谁是报告人? So right now we have the answer shared by group 1 and the presenter is you and then English. Jane. Okay. Ready? Go. Speak louder. Wait a moment. Wait a moment. Yeah. Now you can continue. No problem, keep going. Okay. So how you compare this? Which one larger? Number one larger, right? And how you have the equations, the two equations? From which model? PPT and PPT and video, and also the source. I mean the source coming from which model? I mean the original source to have the formula. Yeah, M1 from the presentation is okay, but MD1. You find it, so find it based on what kind of model? It should be MG1, right? And MG1, can you let us know the formula of the original MG1 formula? Yeah, MG1 formula, so that we have the queuing delay. Can you show the results MG1? Can you show that one? Yeah, sure, you can show that one. No. So which model you apply? MG1, right? And which equation? System time or queuing delay? This one, right? And for this one, why? We can apply this one to have the result for MD1. Right? So how to apply this one to have the result for MD1? This one is the service time, right? Okay, so how to apply that one to this? To have the formula for MD1. So maybe you can find it later if you have a reason. You can share how to find it with the other groups. All right. Okay, that's it. Thank you. Or maybe so maybe right now no microphone, no juice. So for microphone, so good too. Any comment about this problem? Want to have for the further comment? Yes or no?
General approach, because And m is both exponential and...
Yeah, m is exponential, g is the general one.
Yeah, and we need to find the difference between m1 and md1. And I was like, okay, if I have two exponential queuing systems and one with like the degenerate one, then of course the average time of the degenerate one is better because we have...
Sure, maybe you can measure this further. You can measure further based on your idea, and because we need to have some concrete comparison, so you can check it further, sure. And for Jen, it's you, Jen, right? So I'm not sure. So who's serving as the presenter later? You can show you are the presenter online group for the discussion. And wait a moment. And good. 3 or 4. Which one ready to discuss problem 2? Join? Poll everywhere? Oh, you mean this one? Share, you need to share. And also you need to turn on your microphone. You don't have any idea? So Microsoft account, you can try a Microsoft account. Microsoft account. Or maybe you can create one. Oh, maybe you don't have a Microsoft account. Or maybe you can create your own account for Skype. Yeah. So later, if you are ready, you can do that. Okay. And how about use any account on Skype? So you should have the account so that it will be easier to illustrate your idea. Yeah, sure. If you have it, then you can share your idea. So you can join over there. But how to show it clear? And turn on your microphone there. Turn on your microphone there. Your microphone of Skype. Yeah, turn on. I saw that you are the speaker. Turn on. Yeah, turn on. Yeah, so you see? Right? All right, so go. MG1. Reason? flexible.
As it allows general service and distribution, making it more realistic for a queue system where the transmission can have varying data.
Okay, so general and flexible.
Yeah.
Oh, maybe because of the. Yeah. Okay, so good. So reason for the second problem is MG1 is more general and flexible. So it can be applied to analyze ARQ queuing system because ARQ queuing system, should we fit it to MM1? Possibly, but MM1 it's a narrow scope and the MG1 even narrow scope. So of course we prefer the model of MG1. All right, so these are reference answers. Reference answer to all of you. And right now, it doesn't mean after discussion then it's done. For all of you, you need to use the previously discussed answers to key in. And if you feel it's somewhat difficult for you to have the answer on PowerPoint, that's fine. You can write it down and you can take a picture and send it to line group if you want to do so. It's okay, but you still need to mention something on PowerPoint. And so that you can have a link. Well, you can refer to the answer on line group so that you can check my answer there. That's okay. This is the second approach, the alternative approach. If you don't want to do so, you want to have the direct answering on PowerPoint, that's fine. All right, so that you have 3 minutes to key in your answer. So this one, check, and if you want to answer on this, sure, you have 2 problems. For both, you need to provide the answers, okay? Even you group 1 provide the reference solution to problem 1, you still need to have an answer for problem 2. Okay, likewise for the other groups, you need to provide answer to the 2 questions. And go check it 3 minutes.
Yeah, it's still like the past one. Do it.
Okay, so maybe something wrong, let me use this. This one, is it okay? Sure, you can take a picture and send it to line group if you want to say something like that. So that's why I did have the alternative approach by using take a photo, send it to line group. But you need to say something, oh, my answer is put on the line group. Yeah, but for you and for you individually. Yeah, you should send yourself and she should send her. And so that the TA can identify, oh, these are the answers from you and from her. So each one needs to provide your solutions. All right, for both questions. Not for your group only. Not for your group only. Provide your answer for yourself. So let me check, finish. Okay. Let me have for 2 more minutes. If you have correct enough answers, then you can receive 5 points for each problem. Or otherwise, you just receive 3 points only. If you don't have any answer, then it's 0. So at least you need to provide your reference solution there. So you can keep finishing this, and then you can take a rest. So let me make sure this one finished or not finished by you. If not finished, raise your hands. This one. You need to click on submit. Submit. Check it. Right? And it should have a message, done, all done. So, right? Finally, you will have a message, all done, replied by the system. You see, 1, submitted. So, still 5, not finished. Check it. Finally, you need to click on submit. Submit and so that you finish it. Or otherwise, maybe, oh yeah, it's true. So check this again. If you fail to submit, try to click on submit and so that this one done. You see 10. Let me make sure anyone else not finished. All right, I assume it's done for all of you. All right, we have a video talking about overview. And about the first video, overview. If you ever check it, raise your hands. First video. First video talking about overview. Talking about this. First of all, the notation included in that video. It doesn't mean, oh, included in that video, so I won't repeat it. No. In the past, maybe some students let me know, oh, Professor, you asked me to check the video, so it won't be necessary to repeat. So I just want to make sure for the content here, acceptable by you? If yes, then we move on. And if you fail to catch up, sure, you can check the video. And so that we will pass on the notation. And this notation assists us to have the analysis to MG1. So finally, the goal for us is, we have the result, but why we have the result? First of all, the task will let us have for the result. Maybe the task will also provide you some derivations, but not the detailed derivation. So how to have the detailed derivations? Okay, and likewise we have the system length, system time, queue length, and waiting time in queue. And we can find one of them, then we can pass on the previous relationship similar to M1 to have the result. Maybe apply the details law, or maybe apply the relationship between the time. system time equal to waiting time in queue plus the mean service time. All right. And finally, let me get back to the question. Good one, evaluation. We have the formula here and apply one of the formula here. So how to apply the formula to have MD1 queuing delay? Any solution? No, right? So later, I will try to check the content to illustrate that. In fact, this one, we are asked to have the waiting time in queue. We are asked to have a waiting time in queue. All right, so waiting time in queue, follow the formula here. And the B means the service time. Second moment. Of the service time. All right, and second moment of the service time, normally we have the service rate. And service rate, we can denote by mu. So service time, it should be 1 over mu. And this is B. And actually, B squared for MD1 is this. Right? So apply this, we will have a lambda multiply this and over. Right? And so that we still have this. Rho here. I'm not sure, but previously for MD1, your formula MD1 like this. Yeah, correct, right? Equal to this one, right? So that says we can apply the formula of MG1 to MD1 here. D means it's a fixed service time, so that's why B and B squared. We have B equal to 1 over mu. Why? Because it's a fixed value. And this one, denoted by service rate, it's a fixed value. Likewise, B squared for D is 1 over mu squared. So we have the result for MD1. And MN1 actually, we have the results already, right? Actually, it's that formula without 2 in the denominator. And that's the result for MM1. But for MM1, how to have for the MM1 based on the formula here? So this is MG1. And how to have for MM1? And MM1 we have M. It's mu, so we have this. Right? And for the second moment should be this. All right, and then you can find what's this, and substitute into this. And likewise, you can find this solution should be identical to the original MN1 queuing delay. All right, so you can try that one. Well, Okay, so this is the result for MG1 and MD1 and MN1. Even I don't have the results for MN1, but follow the current result without any supplement. We've gone through review of probability theory and statistics, and traffic theory specifically per song, and MN1, MNS, and MG1. So look at this. I'm not sure right now, can you join this? So then we use this again. Maybe one of you finish this, but okay, let me know. After for all the systems here, do you think they are challenged? So challenging to you? Okay, good. Somewhat yes, I think that's true. But if everything is okay, that's fine. Somewhat yes, fine. You need to review and check it. This is the results in chapter 2. We focus on probability theory and statistics. And also we have the extension. And some of you try to pick up the real life example. Fine, good. Yeah, that's correct. You need to have more time to go through the content. Sure, just follow your idea and go through the content, but maybe I have the next question. Let me check. So I think finished for all of you, right? So let me check the next question. Next question is about the task book. I want to check your status, this one. So right now you can see it, right? No. They should find your way to have the task book. Alright, either you didn't find it, but it's okay, you should have your own task book because we still need to refer to the content of the task book. Alright, none of it but that's okay, you just do your way. But I will have some content in the task book, so do your best, let me have that. Now, if I ask you to check here for supplement 1, matrix geometry approach, and the supplement 2 is mean value approach to have the polar vector formula, PK formula. And right now I go through the content directly. And actually, the content here provided by, actually has been delivered by me through the video on YouTube, you can check it. So, if we have some definition for x sub n, and then we can pass on this matrix to have the result. I go through quickly because these are delivered through the video. And also based on the Z transform, we can use the transform equation. Transform equation here. And based on the transform equation, we can find the new system size. But to find the new system size, we need to get these. Transform, but the derivative and set z equal to 1 so that we have the result. But look at this. It's lengthy. Who derived this? It's me. It's me. So, it's tedious and also be passionate and folly. We will have the results, this formula. It doesn't mean I ask you to I understand totally, but I ask you, oh, okay, it takes time and it's tedious, and maybe be careful for you will have further results. All right, so for this one, if you want to listen to someone to explain to you, sure, second video. All right, you can check the second video. Maybe even the second video, I go through something quickly. But I really have some important points. So this is the first supplement. And the supplement here, I should let you know, this is the formal approach employed by the task force. So if you want to know the content of the task force, sure, you need to follow this. And of course, I assume you have the task force. So I do not repeat the content in the task force. I just follow maybe some of the results, but I need to let you have for the extra details, and I let you have for the extra details. So that you can know why we have that one. All right, so this is the first supplement. And if you want to know more, then you can check the video. And normally, I expect you to go through that video, and so that you can understand something. All right, so this one, I understand it's true that to upload the video to YouTube, so that no chance for you to go through that video before you come to the classroom. So first one, I don't know the points roughly. And the second one, same, but different approach. This one, and this approach, in fact, we need to have the well-defined notations. And we base on the concept to find average. If we use the concept of probability theory, we will define, probability. And so that using the concept of expectation to have the result. However, we have a bar. Bar normally means it's time average. Time average says, as time goes, we have the value, right? And how to have the average? We base on the area. Area over the time you observe. And then you can find the mean value. And this mean value, normally it should be equivalent to the in-sample average. But sometimes, maybe for some reason, we don't have the equality. If we want to have the equality, we have some specific condition, and we call it a godity. However, I skip that one. I assume it will be equal, so we have the direct application. Time average equal to in-sample average. So these two, they are different way to have a mean and the second moment. But right now we think they are the same, so we apply the concept. So this is the first one. Apply this concept, and actually we can derive the formula. Why? Look at this. Based on the current description, same. You just follow. You just follow the video, then you will know how to achieve it. But before I go, here one. Actually, cover in the supplement here, and also included in the video. And actually, X bar is B bar, please, and B bar or B square bar or X square bar, we have this. 2 over mu square, and substitute to the formula, then we have this. Then explicitly, this one larger and this one smaller, because it's a half of the N1 queuing delay. Alright, and actually only to N1 and D1 in fact to the others. So you can apply to the others if you have your own idea how to do. Well, I still some relationship because you can check that video for the details. Then, okay, again, I don't want to explain to you. No, I am going to repeat it so that you can check more. So the current problem will be this one, residual. Residual time, residual time. So how to have the residual time? What does the figure here? Oh, residual. Residual means the remaining time for that customer to be served. Well, if you come to the system at the time instant here, oh, okay, because of so remaining time here, the last time remaining time, so it will be aligned with the slope of -1 to 0, and then we have the last one for the service. So we have the sawtooth to represent the residual time. We want to find the mean residual time. How to do? It's area. So you can find the area and over the time you want to observe. So you can have the mean residual time, this one. Right? And we have some specific relationship, and that relationship actually is this. If this, and then we can rewrite and follow something like we have the physical meaning. That's all the physical meaning, but we can have some relationship like this. Here, so that we have this. And something to the previous relationship, we can have the DK formula. Now, this is a different approach we call mean value, and the mean value here based on the time average concept to have the result. And the next one, once we have the result for MG1, so how to apply the analysis, this one. Here we have the details for you. If we have the real ARQ and the ARQ, how to have the delay analysis. Here we illustrate. We need to find second moment of service time. If we have ARQ, this is a way to find the service time. If we can find it, then we can use the MG1 to have the result. And for example, the mention of this MG1, it's general, it's flexible. Because of general and flexible, so we simply have the second moment of the service time. If we can meet the way to have the description, then it can be described by MG1. So, fortunately, ARQ system, yes, we can fit that one to MG1 by finding the something like the equivalent second moment of the service time. So if we have it, then the problem can be solved. So this is the scope we want to let you know. As for the others actually know, but we already have some possible extension. Yes, MG1 actually can include several types of applications. So look at this. If you're using some shop, is it possible? Oh, but they are on a vacation. It's possible, right? So the key model should include that real life example. So very true. If you want to make it real life application, you can try to include model with several vacations. So yes, you can extend further, but I just truncate the remaining one and let you know the title. So if you are interested in this one, you can try to check that one. Alright, so supplement 1 and 2, I provide the video for you. But supplement 3, actually, if you are interested in, here we can apply Little's law or Little's theorem. So the supplement here that we have the possible value. In fact, coming from the same material for the second supplement, but it's a topic to model and Little's theorem. So how to have it? Here. We have some description and maybe some limiting sense. And also if we have some measure to assess something like this. And we can try to base on some concept to find, oh, okay, yes, it's true. Little's law will be valid. Alright, I just go through quickly and we have supplement 3. You can check for details so that you will know, oh, okay, yes, it's true. We will have the little slow. But here I emphasize, we can have the way, even it is not the rigorous one, but this we can verify regularly to show, yeah, it's true to have the little slow or little theorem. However, I want to emphasize application of little theorem. So how to apply? Look at this. In the past, I ever didn't know. I've ever didn't know. Here, we can have the system focus on Q. Q and what is time in Q? Server and service time, right? So the system should be the whole system? No, it can be the subsystem. And we have actually can fit different systems, queue and the server. And how about the entire system? Yes, it's okay as well. And the next one, the second example. Actually, if we have a given example like this, is it possible to apply little slow? Generally speaking, you need to check feasible or not. But if you want to have an answer, you can try. And you can use a different way to validate is it okay or not. But I don't know, oh, okay, for the current problem, since it can use, so we have the time directly and try to apply little slow to have the size. And others. So you can check this to have the possible application of little theorem or little slow. And of course, the task will let us have for the MN1 case system for sure. But say I truncate this so that it will be necessary to have the further reference to this one because we have the results already in our task book. However, here, if you want to know more about the Poisson process here, we have many ways to have the description how Poisson process can be applied to the field. So you can try to check it. And I stop here, and if you are interested in the remaining one, you can try. And that's all. So these are the discussion for chapter 2. We gotta have for the content covered by the task book, and also we gotta have for some supplements. If you want to have more results, of course, you can check in detail. Specifically, you can check those videos to have the idea why we gotta go for all the possible models. And finally, if you are Taiwanese, you can try to check the videos. Video in Chinese. So I don't have the video on YouTube in Chinese as well. So you can check if indeed you want to look at and sorry have some content in Chinese delivered by Chinese. I think you can try. All right, that's all. So these are the discussion for chapter 2. And from chapter 1 to chapter 3 are well assigned. It doesn't need a sign. Well, that you have for the reference exercise. So you can try to select. You can try to use those selected problem to check your familiarity. If okay, after going through the content, you are able to answer those selected problems. I think congratulations to you. You understand that. All right, that's it. So this is a discussion for chapter 2. Well, actually, I need to rearrange it, but actually, we'll focus on the content of chapter 2. And this chapter we will that it have the mobile radio propagation. So, what's the model of mobile radio propagation? Well, we will talk about wave. So, wave actually we will have a wavelength, speed, frequency, and also types of waves and radio frequency band, propagation mechanisms, and the others. So this chapter we will have the discussion like this. First of all, wave. In part, it's the EM wave. So EM wave should follow this. Oh, the speed actually is light speed, but we can have the wavelength and frequency. All right, and speed, of course, currently we have the value. And if so, EM wave, so we have the current is EM wave. FM radio EM wave, cellular it's EM wave, KA and satellite, and the ultraviolet light, they are all EM waves. Because of the common feature, we can fit the formula speed equal to wavelength multiply frequency. So you can check AC current, what's the frequency? This frequency, and so that based on the formula, we can map it to the wavelength here. If we have the wavelength here, so look at this AC current, the corresponding wavelength extremely large. And how about cellular? Oh, even not extremely large, but we have the size, around 40 centimeters. And the others, ultraviolet, it's really small wavelengths. So even we have the EM waves, but they don't have the same nature. And so that we can apply different nature to have the different things. So this is the phenomenon we want to illustrate to you. And so that we have these types of waves. We will have a ground wave. And a bit higher than we have a space wave. And furthermore, we have the sky wave. All right. And this is Earth, so we have the different layers. And the layer we have this troposphere, stratosphere, and mesosphere, and ionosphere. And we have all of these. And all of this allow the web, specifically the web, to have the different behavior. But for this layer, we only have a space web, one web. As for the others, possibly we have a sky web. Alright, so because of web and layer, we can have the possibility to use it to carry the information so that we have the way to have the communication. So this is the type of wave. Well, maybe for Taiwanese you want to know what it means, ionosphere. I try to read to Cambridge Dictionary, this one. All right. And actually we have the others. And how about this? Here, something like we have the definition, the range, and which layer? I don't know its layer, right? This. Mesosphere. This one. Stratosphere. All right. The following is this here. All right, so we have a different layer, and so that based on different layer, we will have the different mechanism to transmit the EM waves. So I don't have all of this, and then we can go to the next one. Well, so we have a lot of EM waves, but they don't have the same nature, and they don't have the same nature. We can pass on the frequency to have the frequency band, and the frequency band starting from 300 Hertz, and then multiply 10. Right, multiply 10, and based on this way, so we can form the frequency band from extreme low, ultra low, very low, low, and then medium high. vary, you see, very high, ultra high, super high, extremely high, tremendous high. And so that we can have the corresponding ratio to represent the frequency band. Well, if we have the way to have the frequency band, then we can associate the frequency band with the corresponding wave. Ground wave, ground and sky wave and space wave. So for the previous waves, we can pass on frequency band to have the classification. It doesn't mean we have a one-to-one mapping, but for the current frequency band, yes, only ground wave. And the space wave here. For the middle one, actually, sure, we have sky. It doesn't mean shy. Sky. It should be sky web. So sky covers the two, but ground and sky for the medium frequency band, we still have ground and the sky web. Alright, so these are the frequency band, and the frequency band suitable for the ground wave transmission, sky wave transmission, and space wave transmission. Alright, and that's all. But in the following, we have some propagation methods: reflection, and scattering. Alright, because I guess we don't have the textbook, but you can look at the internet for sure, but I allow you to use this way to know what it is: reflection, and scattering. So right now, I allow good one. This is easy. Maybe good two. You just have to remember, check what it means: reflection. The mechanism of a reflection and good four, diffraction. And good 1 and 3, check scattering. Alright, and you can look at what it means. It doesn't mean, oh, okay, I want to take a rest. No, I just ask you to use this way to think about what it means, and so that you won't feel sleepy. Alright, so check it. Let it have 5 minutes to check these. And later, if we have time, then I ask some of you to share what it means: reflection, and scattering for the 3 terms. Sure, you can feel free to discuss with your neighbors. Emphasize your mission first. Scattering, it should be good 1 and 3, right? And refraction by good 2, and diffraction by good 4. Identify the term first, and then let us share, or maybe listen to the other, and so that you can know, oh, what that means, all the terms here, and so that they are propagation mechanisms. Okay, go and check it. Maybe in the past, I don't know if I don't have the textbook, someone on the internet. I'm not sure, maybe not the normal network, but still they can find the book and download the book. So if you want to have it, you can try. But I don't have that way to access that book on the internet. Yeah, but someone get it. Yeah, so you can try a possible way. If yes, maybe you can share their way to the others. I'm not sure it's legal or illegal. Yeah, you can try to find. Maybe in the past someone let me know, oh, they can find it on the internet. So if you don't want to buy it, at least you can try this way. Yeah, and this way, why don't they have the book for sure? So maybe if you can try to share not directly, but at least you can try one by one to the other members. And then you can try to use that way to have the way to access, maybe not access, either access and then you can download. Yeah. I saw that it will be okay for all of us to have for the reference content there. Okay. So next one, it still stays there, okay. And hopefully you can have get closer to have the discussion directly. Don't worry, don't be shy. All right, don't be shy. Just take it easy. So previously our presenter there. Okay. So next time, if we have the sharing, I will assign you want me to serve as the presenter and you. So talking about reflection. What's reflection? Something like, what's reflection? Yeah, and you can look up further for sure. You can. Oh, diffraction? Oh, okay. You want to talk about diffraction, that's fine. All right. So later, you just select one. Reflection or diffraction. And for you, scattering? Okay, sure. So then we mention group 2 and 3. Ready? Ready to have the discussion about the term in focus? Yes or no? If yes, same. Using Skype. So that means go to Skype first. And this time, no one on Skype except me. And go to, do you have the account? And press from good 2. Share your screen and let me know how you want to talk about the so-called diffraction or reflection. Either one is okay. So ready? Set it to mute. Are you ready? It's okay for you. If not ready, how about group 3? But time's up, so maybe next time this Wednesday. So this Wednesday we will have the sharing from group 2 and group 3 and talking about the propagation mechanisms. All right. And possibly even we finish the discussion for chapter 2, but try to go through the content of the slides and the videos possibly, and so that you can fully understand the content of chapter 2. And I will post the selected problems for self-exercise. Self-exercise, I may select some, and next time we can pass on those who have the direct exercise. So be prepared to know the content of chapter 1 and 2. I possibly select some problem to ask you to have the direct exercise for those selected problems next time. All right, is it okay? So before you come this Wednesday, hopefully you can review chapter 1 and 2. And I may select some problem and ask you to do. But before we ask you to do that, at least we check the contents first. Propagation mechanism, and share by good 2 and 3. And don't forget, good 1 and good 4. One of you serving as the presenter, you need to let TA know you are the presenter, and so they can receive the bonus of 2 points. All right. For good 1, it's you, right? Okay. All right, that's all, and see you next week. See you next time this Wednesday. Bye-bye.